All right, so in part B of this problem, we are going to want to show that the critical light to mass ratio, uh, L of R over M of R needed for convection looks like the equation written down on the page. And the hint that we are given is that we will need to express radiation pressure in terms of T. Luckily, there is an equation for that in the textbook in chapter 5, specifically equation 140 in chapter 5. So you can go ahead and take a look at that for yourself. But it is an expression for radiation pressure, or Prad, as a function of temperature and only temperature. All right, so that's a 4 sigma SB Stefan-Boltzmann constant times temperature to the fourth power divided by 3 times the speed of light. We're looking for a critical light to mass ratio where convection will just be equal to radiation pressure. So what that means is that the temperature gradients of those two are going to be equal, where neither radiation or convection dominated. They're equal to one another. So it's supposed to say rad, and then also dTdr. This one being convective. So we're going to use basically the two previous equations. The equation that's given to us, the equation that we found in part A, and this is to part B. Sorry if that wasn't clear. Or I guess, sorry, question 3, part B. Set those equal to each other, so I'm just going to plug a bunch of stuff in now. 3 row Kr, so K is an opacity, the R stands for Roslin, so it's the Roslin mean opacity, so just a type of average opacity of the star. You can think of it that way. And I'm just copying this down, sigma T cubed pi R cubed. I'll give myself a little, oh, that is not what I wanted to do. Okay, we'll just leave that there. This is equal to, oh my gosh. This is equal to the convective temperature gradient, which we found in part A to be gamma minus 1 divided by gamma temperature divided by pressure, dPdr. Okay, so we have a dPdr right now. We don't want a dPdr in the final answer. So what is our favorite way to get rid of dPdr? Well, let's use hydrostatic equilibrium to get rid of it. So I just want to substitute out that one quantity, keep everything else the same, still gamma minus 1 over gamma temperature times pressure. So we normally think of dPdr as being rho times little g, or gravitational surface acceleration. But let me just go ahead and substitute gravitational surface acceleration, or rather just gravitational acceleration for what it is, and that is big G times mass enclosed. That's why it's a mass as a function of radius divided by radius or distance squared. All right, so we have 3 things that are all equal to each other. So the far left is equal to the far right. So we can actually start canceling out things that appear on both sides. So we have 1 factor of rho in both of them. And then we also have an r squared in each of them. And I think that's the only thing that's going to cancel out. So now, so I'm going to do a lot of algebraic rearranging. So because we're solving for a light to mass ratio, so I'm going to want to take this L of R that's on the left, divide both sides by M over R, and then move all other constants over to the other side. So I'm not going to cancel out anything or even really evaluate anything yet, just rearrange things. But just to get L of R over M of R isolated, that means I'm going to flip everything else over to the other side. Oh, and then by the way, we have minus signs on each side that are going to cancel out. So we're left with plus 64. Stefan-Boltzmann constant, T cubed. Stuff is basically just getting flipped. Pi that's really far away for some reason. 3 divided by the Roslin mean opacity. with the gamma minus 1 over gamma, temperature divided by pressure, and then just big G all by itself on the end over here. Good. And then really the last step is to substitute out certain constants and variables so that we can substitute in our radiation pressure equation that we have from before. So we're basically just going to borrow a factor of 4, borrow a factor of 3, borrow a factor of Stefan-Boltzmann constant, borrow a factor or insert a factor of speed of light, and mainly borrow a factor of t to the 4th power, which is all conveniently there because we have a t cubed multiplied by another factor of t. So you can try that out for yourself. Check to make sure you get the same thing as me. So gamma minus 1 over gamma is equal to 16 pi. Reunite the 16 with the pi. G times C, Rosalind mean opacity, times P rad over P. Those p's look crazy. And then just to make sure that our equation looks like theirs, we can just go ahead and put a little crit subscript on our light to mass ratio. And again, the reason why it's critical is because we dictated that the radiative temperature gradient would be equal to the convective temperature gradient. It's kind of fun having a lot of different colors. Okay, and that concludes part B.